Okay, so now I'd like to talk more about this notion of harmonic analysis. And this lecture is just a little bit giving you an introduction to this whole topic. And the basic idea in harmonic analysis comes from, I think the main methods really come from like signal processing. So when we have some like a very, let's call it like a very complicated signal coming from, let's say, a sound signal, or it could be a light signal or something like this, we'd like to usually decompose this signal into components that are maybe easier to manage, like understand a bit easier, or like maybe you're going to read some information or hidden information from the signal by decomposing the signal into some other components. And this is where Fourier analysis comes in very handy, because you can take a very complicated looking signal, like a fractal type of a signal, and using these basic methods you can actually get this type of an information. So let me kind of start this. So we have harmonic. Let's call it harmonic analysis. Analysis, and what we basically have here is this notion that we have a like very say complicated looking function. You could think about this as a signal on the real line. So here we have r, and it could be any kind of a function f with certain properties. So it could be like given as a function f of x, and the Fourier analysis allows us to basically approximate this function as a sum of more simple functions with certain like wavelength, for example. So what we have here is that you could think about that. Okay, this function, when you start to approximate it, it starts to maybe you could think about it. Okay, you have this this kind of oscillation at some point, and then other points you could like add. Oh, sorry, this is that maybe this is better, and maybe use another color for that. That you, when you start adding functions of different wavelengths, like for example here with this this type of function, and maybe with another color. This should be, yeah, it's a bit messy picture, but basically what these functions, these different colored functions are, they have certain like wavelengths. So let's say, for example, let's isolate one of the like the blue function over here, what we have over there. Let's say this function over here, this blue function that we isolated, then this function over here has certain like frequency at which these jumps occur. So this is, let's say, we could call this as the length that you have here. You would call this maybe the 1 over the frequency that you can see over here. So it gets like very when the frequency increases, this length here gets smaller and smaller, because you can fit more of these jumps into a small space. And then at the same time, this height here that you could see, like height of each of these, this could be called the amplitude. And this blue function is kind of like our wave that we would like to decompose our function f. And the typical functions you usually use in this kind of a setting are really these kind of, for example, cosine functions. So this could be like, you could just think about that this is some function cosine, maybe at 2 pi k of x, and then maybe it has some amplitude, ak. So that would be like amplitude ak, and the frequency, this would be, let's say, 1 over, I don't know, you could call it 1 over k, for example, if you define the k to be the frequency. Then this is like the type of functions you want to consider in this kind of notion. So Fourier series then looks something like this, that at x in R we want to find amplitudes, let's call them AK, k in z, such that, let's say, f of x can be written at these frequencies. So if you take this summation over all the amplitudes, k in z, ak, and then you get cosine 2 pi k of x. So this is what you'd like to do, that basically decomposing the function into this sum. And this is possible. It's possible to do this, but it depends on how nice your function is actually. Like it's in the lecture notes I've added a bit more references on like things, and there's also various like heuristic explanations about when this is possible. But typically what you can expect, so typically if f is nice enough, and this is really depends on the kind of theory that we are considering, this is possible by choosing this ak to be, usually you'd like to maybe this function to be, let's say, of this form, that it's a, let's say, if it's a, let's assume that this is a periodic function, for example, so 0 to 1, like a periodic function, that you would choose this kind of coefficients, f of x cosine minus 2 pi k of x dx, where this would be, let's say, the Riemann integral. So these are the types of coefficients that you would expect then to be appearing in the definition of the thing. Let me actually write. I could maybe just in case write like y, so that we don't confuse with this x that we have here. So that's the type of coefficients that you expect, and this is kind of, there's a name for this. This is called I think this is called cosine Fourier transform, which is usually written, I think sometimes one uses this notation, cos of k. At the point k, you wrote this cosine transform. So that's when you have a nice enough function, you might be able to choose the coefficients in this way. But then it turns out that actually in more like theoretical analysis, what we usually do, using the cosine everywhere makes it slightly more technical, and also there will be some issues with certain types of functions, with certain like very exotic properties. So that's why usually one complexifies the problem. So instead of sunning the cosine, or instead of splitting your function into these sums of these cosines, you also add the possibility of creating the function within the complex plane. Because the idea with this kind of Fourier analysis is to be able to add functions that have more positive and negative signs. So there will be some type of a cancellation going on, that you, in the end, you end up to a real number. Let's say a positive number, like in this situation. But you can do the same in the complex plane. You could add complex numbers together, and then they sum up into some number which is then, let's say, a real number. So it's possible. And so that's why typically you use this idea that you use this, first of all, the Euler's formula, 2 pi k I x. I think this is, or maybe I could xi. So the Euler's formula with this cosine 2 pi kx plus I sine, let's call it Euler's formula, sine 2 pi kx. And then you hope that is it possible to write the function in this something called Fourier series. So then one replaces the cosine series by this kind of Fourier cosine Fourier series by this expression, that whether this is possible, that this you could write this as k from z with some amplitudes. Let's call them bk now, bk, and then e to the power 2 pi kxi. So is this possible to write it in this form? And where here you want these coefficients to be something called Fourier transforms of k, which we define to be integral, let's say from 0, 1 of f of y e to the power minus 2 pi I ky dy. The same way. So that's the question, that whether it's possible to do that. And that's the basis of Fourier analysis. So in certain types of situations for certain nice enough functions, you are able to do this. And there's a convergence. Maybe sometimes it's not converging everywhere. There might be some exceptional points where it fails. And that's why you need to talk about something called Lebesgue integration, for example, Lebesgue measure, to be able to make that convergence, or really make that sense. But this is not the topic of this course. We don't go into measure theory and the real line. But instead, we want to talk more about the group ZB. And in that situation, we basically develop the same theory that you do in the real line, but the advantage of using the group that we are missing a lot of the technicalities that come from the, let's say, some very exotic functions that have certain crazy properties, that where this Fourier analysis might not be so clean. So in the next lecture, I plan to go into this topic of Fourier, or the Fourier transform in ZB. So that's all. Thanks.